Lab 5, Magnetic Braking with Faraday and Faraday's Law by Nikita Crisp. I'm in Physics 2212 Section P with Professor Wise. So, the purpose of this lab was to help us prove Faraday's Law through observing a magnet and watching it fall through a conductive tube of foil. And while we did that experiment, we collected observational data so that we could later compare it to computational data. And this computational data we would get because we were tasked with modeling the magnet and the tube computationally in GlowScript code, which we'll get to later. And then finally, we were supposed to compare our computational predictions with our actual data. And so for my actual data, when actually doing the experiment, I got, for trial 1, 1.75 seconds, for trial 2, 1.68 seconds, for trial 3, 1.60 seconds, trial 4, 1.79 seconds, trial 5, 1.72 seconds, trial 6, 1.56 seconds. And initially the way we went about this was taking a video with the phone like the lab suggested, but we didn't see any millisecond timestamps on the video, so we decided to just do it with a stopwatch instead and just watch visually when it entered and exited, which was probably a bit of an error on our part, but we'll get more to that later. And the average of all of these trials ended up being 1.68 seconds. So for observations, we observed that the magnet falling through the conductive tube fell a lot slower than the magnet would have fallen through a plastic tube or just to the ground in general. This meant that there must have been some induced forces on the magnet that prevented gravity from being the only force acting on it. So therefore, there must have been a magnetic force acting on the magnet that was induced due to the conductive aluminum foil surrounding the magnet on its descent. Alright, so further observations. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the falling magnet would then fall as if it were falling normally, and the only force acting upon the magnet would be gravity. So the magnet falling would fall as you would expect if it were in a plastic tube or just, normally. And the second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So I said that the ring currents in my model would be much larger because this would greatly impact the magnetic force felt by the magnet. For coding, for the coding portion, initially I created a graph for velocity versus time. Then I modeled the tube of aluminum foil and the magnet. After that, I created a function in order to calculate the magnetic field of the bar magnet, and then another function in order to calculate the magnetic flux. And then finally, I created a simulation loop that would help to model the motion and help to visualize what is going on as the magnet falls. So here is the running of my program. You can see there, you can kind of just see the magnet fall. I'll play it one more time. Yeah, so essentially that's how the magnet would fall, and here is the resulting graph of that. You can see it's slightly curved, a graph, but it's almost linear. So this tells us that there were definitely more than gravity at play, because if it were only gravity acting on this, then you would expect like a sort of an exponential graph, but because this is almost linear, this tells us that there is more than gravity acting on the magnet. And so now to talk about the simulated time of 0.3 seconds and how different that is to our actual data. This was likely due to the fact that we calculated the time with a stopwatch and not with a video. So there was some error there. But yeah, thank you for watching and have a good day.